In this case study, I'm going to talk about the design of a C-band VCO. In a number of presentations, I'm going to go through how this circuit was designed and how it achieved its performance. This circuit, as shown here, and pretty much that's the entire circuit, achieves state-of-the-art performance. It's a tunable oscillator that operates from 4.4 to 5.5 gigahertz and produces 1 milliwatt of RF power. So there are many things that go into the design of this oscillator. So let's start the journey. In this presentation, the first of the series, I'm going to first of all talk about the reflection oscillator principles, the common base Colpitts oscillator design strategy, and this circuit is a modified form of the common base Colpitts oscillator. Then I want to talk about reflection oscillator operation and why we have made historical choices, and eventually I'm going to talk about small modifications you can make to that design strategy to achieve improved performance. Then I'm going to separate the oscillator out into its component networks, a resonator network and an active network, and talk about their topologies and basic admittance characteristics. And then we're going to talk about the point of oscillation. What establishes oscillation? What establishes the desirable characteristics that we want? Here is our basic reflection oscillator. We look at oscillators two ways. We look at them as oscillators which look like feedback networks around a gain stage, and we look at them as reflection oscillators. For microwave and RF oscillators, we can always look at them either way. At low frequencies, when we're using operational amplifiers, we may need to consider that feedback form and not this one-port reflection oscillator form. But for RF and microwave oscillators, we can consider them either way. The ideas we have about stability usually come from the feedback form, and when we look at the feedback form, we can make use of a large body of linear control theory to establish oscillation conditions, such as the Nyquist theorem. However, when it comes to designing competitive oscillators, at this stage of development, it is best for us to look at the reflection oscillator form as shown on the top here. Perhaps in 10 or 20 years from now, or maybe even next year, our CAD tools may have evolved to the point where we can consider a more sophisticated approach. But there are many trade-offs that need to be made relating to efficiency, that is, how much DC power we put in for a given RF output power, the tuning range for the voltage controlled oscillator, the stability of the oscillator over temperature, the startup conditions for the oscillator. Those trade-offs are best made by humans at the moment. At the frequency of oscillation and at the amplitude of oscillation, we can express the oscillation condition several ways. We can express it as saying that the admittance of the resonator circuit or the tank circuit is equal to the negative of the admittance of the active device, that is, YR is equal to minus YD. We can express it in terms of the reflection coefficient, and this is saying exactly the same thing. We can say that the reflection coefficient of the resonator is equal to 1 over the reflection coefficient of the device. Or, putting it another way, gamma R times gamma D is equal to 1. So all of those are equivalent, and we will hop among these expressions of the oscillation condition depending on what suits us at a time. During our design, we will make heavy use of Smith chart representations, and when we do that, we will talk a lot about the reflection coefficient. But we'll also keep in mind what the Smith chart is telling us about the conductance variations and the susceptance variations. We could also consider this oscillator in terms of impedances instead of admittances. But most of the time, our active devices really do look like transconductances, and so conductances are the normal way of looking at things. We can certainly take a transconductance and with some contortions and circuit design, we can make our transconductance element, which of course is the transistor, look like a transresistance. But it is much easier to look at this problem as a transconductance problem, or just a conductance problem. Now there's some other criteria that we realize must apply. When the oscillation is small, that is when the signal is just starting, a condition that we call oscillation startup, we must have the magnitude of the reflection coefficient of the device greater than the magnitude of the reflection coefficient of the resonator. And as oscillation builds up, gamma d will get smaller. And we would like it to get smaller in a very controlled way, so eventually the magnitude of gamma d is equal to the magnitude of gamma r. And at that point we will also have the magnitude of gamma r is equal to the magnitude of 1 over gamma d. In all circuit design, we begin with a topology in mind. Perhaps that topology is all that we need, or perhaps we have to evolve the topology. But at some point we have a topology that we feel comfortable working with. The circuit that is shown here is a common base Colpitts oscillator. One of the characteristics of this topology is this resonator network here, made up of CR and LR. That is called a resonator, but it is resonant at a frequency below the oscillation frequency of the oscillator. So CR and LR resonate below the frequency of oscillation. Above the resonant frequency, LR will have an impedance which becomes quite large, and the impedance of CR is getting smaller. So the impedance or admittance of that LR-CR in parallel is a capacitance. And the key characteristic that we achieve by using this resonator structure is that the susceptance of that effective capacitance has a slope with respect to frequency that we can control. So it's a very nice idea, this idea that we don't just put a capacitance there, we put an element in there with which we can control both the susceptance and the slope of the susceptance. Now I'd like to show you how this relates to a traditional Colpitts oscillator. Here's the Colpitts oscillator in feedback form. So some of the characteristics are that this capacitance C1 is connected to the input of our amplifier, capacitance C2 is connected to the output, and L3 provides feedback from the output to the input. In transistor configuration, this is what the Colpitts circuit looks like. We have a feedback output between the capacitors, and we're applying the output voltage from our amplifier across L3. L3 is that capacitance LB. But let's step through here. The effective capacitance formed by CR and LR becomes our C1. The inductance LB becomes L3. And the parasitic capacitance from the collector to the emitter becomes our C2. As well, there will be capacitance from the collector down to ground. In addition, we can also add our own capacitance. We would like a topology and a design strategy which minimizes the impact of the capacitance at the collector on the oscillation frequency of our oscillator. By so doing, we also reduce the impact of variations in the load. That is, we would like to minimize the impact of the load on the oscillation conditions. Now, it's not terribly clear that LB provides feedback from the output to the input. But consider this, LB is a common element between the collector to ground and the emitter to ground. The emitter to ground in the common base configuration, and this is certainly biased as common base, the input is at the emitter terminal, the output is at the collector terminal. That inductor is common to both and provides the feedback from output to input. Now I want to talk about our conventional view of reflection oscillator operation. And the view that I'm going to describe now can be used to design successful reflection oscillators. On the top here is our modified Colbert's common base oscillator, and it can be partitioned into a tank circuit and an active device circuit. The tank circuit could be called our resonator network. The device can be called our active device network. And we know that oscillation will occur when YR is equal to minus YD. Graphically, it looks like this. Ideally, what we want in our circuit is for the conductance of our resonator network to be independent of the oscillation amplitude. Now, that is not always a given, because if we look at our VCO circuit, we have a variable capacitor. And the typical way of achieving a variable capacitor is to use a varactor diode, that is a reverse biased p-n junction diode. When we change the voltage across the diode, we will change the capacitance. So we do need to take some care to make sure that GR is independent of amplitude. Oscillation will begin when the magnitude of GD, the conductance of our active device, is larger than GR. Now GD is negative. As our oscillation amplitude A increases, the magnitude of GD will eventually decrease, and the amplitude of oscillation will be determined when these two cross. As the amplitude of the oscillation increases, the magnitude of the device conductance decreases, while the conductance of the tank circuit GR is constant. Looking at the susceptance now, ideally what we would like to have is a rapid variation of BR with respect to frequency. BR is the susceptance of our resonator network, and in our conventional view, BD is independent of frequency. When BR is equal to minus BD, that will define the frequency of oscillation. So as the frequency of oscillation increases, the susceptance of the tank circuit BR changes while BD ideally does not change. As circuit designers, we're free to depart from these if we like, but the further that we depart from these ideal situations, the harder design will become. Let's look at the active device in a little bit more detail. So for our active device, we would ideally like GD to be independent of frequency, and we'd like BD to be independent of frequency. First of all, think about GD. GD is our negative conductance. By keeping GD independent of frequency, we're going to achieve a result in which the amplitude of oscillation is independent of frequency. Thus, this results in constant amplitude across the tuning range, and that is just what we want with a VCO. We want the same output power independent of frequency. Now looking at BD. If BD is independent of frequency, this results in low phase noise. The combination of GD and BD being independent of frequency results in low phase noise. Let's look at the susceptance. This is the ideal susceptance response that we want for our active device. We would like a BD which is independent of amplitude, and of course GD will be dependent of amplitude. That is something that we want. because if GD is dependent on amplitude, that means that our oscillation will build up and hopefully reach a stable point. Now, this situation where BD is independent of amplitude results in low phase noise. Remember, it's when BR, the resonator network susceptance, is equal to minus BD that we have our frequency of oscillation. So if BD varies with amplitude, that means that crossover point that defines frequency depends on amplitude. That means that the amplitude of our oscillation signal determines the frequency of oscillation. So a little bit of noise on the amplitude of oscillation would have quite an effect on the frequency of oscillation. If our amplitude variation, perhaps due to power supply noise, perhaps due to noise in the resistors in our circuit, can superimpose noise on our oscillation signal, that would change the frequency of oscillation. Now, of course, that is very small, but one of the things we're incredibly good at in microwave design is establishing the frequency of oscillation. So if you look at a cell phone, we're operating a cell phone with accuracies of 1 Hertz in 10 to the 9 Hertz, 1 part in a billion. So we achieve some very good performance. And our performance of radars, of cell phones, and nearly everything else at RF is very strongly dependent on phase noise. So we absolutely need to keep the phase noise contributions as small as possible. And by making BD independent of amplitude, we go a long way to reducing our phase noise. And we're going to talk quite a lot about this over the next few presentations. So, in summary, a small variation in BD with respect to frequency is okay and unavoidable at RF, but a variation in BD with respect to amplitude is not. Sometimes we want a variation of BD with respect to frequency to ensure oscillation startup, and this is especially important for VCOs because we want oscillation startup over the full tuning range. The circuit that we're going to design is shown on the bottom of the slide here, and these 3 circuits show the evolution. The first stage, we want to design a reflection oscillator. A classic topology to implement a reflection oscillator is a modified Colpitt's common base oscillator shown there, and the topology we're actually going to use is very similar to that modified Colpitt's common base oscillator, but with a number of extra components, quite a few extra components really. So we're going to look at the resonator network first, and then we'll look at the active network and try and understand what all of these various components are doing. First, the resonator network. So the circuit that we're going to work with is shown on the right. Remember, all circuit design begins with some topology in mind, and a circuit such as that shown on the top right is the circuit that an oscillator designer comes up with after many years of experience. So it's not something that you arrive at quickly. You can get a head start by You can get a head start by being very familiar with the literature, looking at patent applications. Of course, patent applications are things Of course, with circuits that are patented, your company may not want to pursue the same design, but designs and ideas that are in patents often lead to other design ideas. And many of these oscillator configurations are published by academics who don't tend to want to patent them, and so there are a lot of sources for information. So our full network is shown at the top right there. I'm just going to pull out the resonator network and make it a little bit larger and trying to describe what's going on. So it is all about realizing a microwave form of that parallel resonator, the LR-CR circuit. So let's remove some elements from consideration. First of all, those inductors down the left hand side attached to the diodes D1, D2, D3 and D4 are RF open circuits. So they're designed to have an impedance which is quite a bit higher than 50 ohms in magnitude at least. The most obvious difference here is the use of this transmission line resonator, and that transmission line replaces LR in the simplified Colpitt's common base oscillator, and this resonator has much lower loss than the inductor. So transmission line is a good choice here. This is a fairly low impedance line. That's a microstrip line. What is shown here is some indication that the width is very wide, so it's going to be a low impedance line. Another characteristic is that we tap what is called tapping anyway. We tap the transmission line. We do not go directly in at the top of the transmission line. This provides a little bit of impedance transformation. Another significant characteristic are the stacked varactor diodes. To achieve a tunable capacitor, it would only be necessary to use one of these diodes. These 4 diodes are used to increase the RF breakdown voltage, and each of the varactors has a tunable capacitance. And so with D1, D2, D3 and D4 in series as far as our RF signal is concerned, we're able to achieve a tunable capacitor which has a fairly large RF breakdown. Now, one of the characteristics that we want from our resonator network is we want the susceptance of the resonator network to be independent of the amplitude of our RF signal. So there will be RF signal at the top of this stack. By having this stack, we're able to achieve a variable capacitance, but also greatly reduce the variation of that susceptance because of the amplitude of the RF signal across D1, D2, D3 and D4. It is a common trick that is used. You can see that in many circuits. So really things are fairly simple here, aren't they? We have used a number of choke inductors, which are RF open circuits. We've replaced LR by a transmission line because it has lower loss, and we've used stacked diodes. A good designer collects these various tricks that they can use over and over in different situations, not just in oscillator design. So in this design of a VCO, as with all design, we are going to iterate towards a solution. And this design requires both computer simulation and measurements in the laboratory in order to get it to work. So let's look at an interim stage in the design. This is actually fairly close to the final design. We're plotting here the reflection coefficient looking in to the resonator network. You could say that we're plotting the admittance looking into the resonator network, but gamma R makes a lot more sense. So what we have here is a situation where we have a tuning voltage of 3 volts across our varactor diodes. We're looking at the reflection coefficient. Remember, we want our VCO to operate between 4.4 and 5.5 gigahertz. Plotting gamma R, we start off with 3 gigahertz here. We go through a resonance here. Well, I won't draw on top of this line, but we go from 3 gigahertz, we go around this circle, and then here is the variation of gamma R that determines our oscillation frequency. So we go from 4 gigahertz to 5 gigahertz, and we cover about 3/4 of the Smith chart. Our locus is moving in the clockwise direction with respect to increasing frequency. And so somewhere between 4 and 5 gigahertz, where we're having rapid variation of BR with respect to frequency, we want to establish our oscillation condition. Now let's look at the active network. So here is our active network. Remember, our ideal situation is that we want GD to be fairly large in magnitude and then reduce as the amplitude of the oscillation signal increases, and we want BD to be independent of amplitude, and that is a very important characteristic, and that reduces the phase noise of our oscillator. So look at the active network and read through that. You may want to pause. So there are a few elements in here that act as RF open circuits and RF short circuits, and I've identified those here. We have an RF short circuit connecting us directly from the emitter to the resonator network. The resonator network is on the left here. We have an RF short below the base. We have an RF open going off to VCC. So when you start using these RF short circuits and RF open circuits, you see that the circuit has reduced down quite a lot. This resistor and this resistor here bias the base, so very little RF signal goes through there. This is our feedback inductor, and there is some matching here to our load. But one of the big departures from the common base Colpitts configuration, that is the conventional configuration, is the addition of these two capacitors, CA and CB. And in fact, in this design, this is the unique feature. CA and CB can be adjusted so that the derivative of BD with respect to a voltage is approximately zero. Returning to our plot on the top left here, that is, BD is independent of the oscillation amplitude. We want that characteristic to manage noise, to keep our phase noise low, and this is the unique feature of this design. The reflection coefficient of the active device is shown here. Of course, this reflection coefficient is going to change with the oscillation amplitude. So at small signals, when this circuit is driven by a generator at a fairly low level, we can measure gamma D either in a simulator or in the laboratory. The magnitude of gamma D for small signals is going to be greater than 1. And plotting is a bit of a problem on a Smith chart. And so the conventional approach taken is to plot 1 over gamma D. So this is a plot of 1 over gamma D for small signals. We start from 3 gigahertz to 6 gigahertz, so it takes about 3 gigahertz to traverse the Smith chart. With the resonator network, it took about a gigahertz to make that transition. As the amplitude of oscillation increases, this curve moves to the right. And for good oscillation performance, we want to control the movement of that curve. So one of the characteristics we want is that BD does not change with respect to amplitude. That means we must follow a line of constant susceptance, and a line of constant susceptance looks like this. And here's another line of constant susceptance. In a simple reflection oscillator design, we would try and follow that line where BD is equal to 0 and the frequency of oscillation is solely determined by the resonator network. But at RF and microwave frequencies, the parasitics associated with our transistors are really quite large, and so we cannot ignore them. In addition, in this design, the inductor in the base results in an inductance being presented to our resonator network. So we're not able to stay on that horizontal line. So what we want is for the derivative of BD with respect to amplitude to be 0. and we have to follow these lines of constant susceptance, either that line or that line down there. And in future presentations we're going to talk about how we decide which of those we want to follow. Now the point of oscillation is going to be determined by when the resonator admittance is equal to the negative of the device admittance. Or in terms of reflection coefficient, the point of oscillation is going to be determined when gamma r is equal to 1 over gamma d. Another reason for why we want to plot 1 over gamma d. So 1 over gamma d, this curve here, this purple dashed curve here, is going to move to the right as the oscillation amplitude increases. This resonator network will not move as the oscillation increases. Ideally it doesn't move anyway. As long as we've taken care of our varactor diode network, that's the only nonlinear part in our resonator network, that'll be the case. So assuming that gamma r does not change as amplitude increases, this dashed purple line will move to the right, as shown there. The point of intersection defines the oscillation frequency and amplitude. So part of our design strategy as we get more involved in design and get closer to the final design is we want to follow a line of constant susceptance so that we have an intersection point around about here. Now we could follow other lines of constant susceptance as well. In this particular design, this is the line that we follow. And so our point of intersection is in this region here. Now there are some things we want for our oscillator. We want just one point of intersection, and we need that for single frequency oscillation. Now one of the things you may note here, if you just think about this a little bit more, is that our gamma r curve and our 1 over gamma d curve are rotating in opposite directions. And that is exactly what we would like. We like the fact that our active device network has a variation with respect to frequency. That further reduces our phase noise. To see that, let's look at a larger signal. So here is a curve for a large amplitude. I've really had to guess this because I don't really know what that reflection coefficient will be under oscillation conditions. I cannot reliably simulate it. So this dashed curve has a locus that moves in the counterclockwise direction with increase in frequency. Of course, gamma d itself moves in a clockwise direction, as we expect for most circuits. But 1 over gamma d moves in the counterclockwise direction. The resonator network has a locus that moves in the clockwise direction. And it is this point of intersection here that defines our oscillation frequency and our oscillation amplitude. So there's just one point where that happens. And you may wonder why we can build oscillators at all if there has to be an exact point. Well, it turns out that as our amplitude is increasing in an oscillator, the harmonic content is changing very slightly. So if we get close to this point, our harmonic content in the oscillating signal is going to shift just slightly so that we lock in on that point. And we see this in many of our oscillators. Of course, the oscillators that don't have this behavior are simply not used anymore. So it would be possible to have an oscillator that goes into a chaotic state at that point. But the oscillator topologies that we have come to adopt have this characteristic where that small variation in the harmonic content locks us in on that frequency of oscillation. Let's look at this point in even more detail. So these curves, the gamma r curve and the 1 over gamma d curve, are going in opposite directions, so they fly past each other very quickly. That even further reduces our phase noise. So this oscillator, this discrete oscillator, has very low phase noise. It is difficult to achieve this with an integrated oscillator. although as people become more sophisticated in design, I'm sure that we will. Okay, summarizing, our oscillation condition is that YR is equal to minus YD. That's the same as saying that gamma R is equal to 1 over gamma D at oscillation. So GR is equal to minus GD, BR is equal to minus BD. So note that the derivative of BD with respect to frequency is greater than 0, and so the derivative of minus BD with respect to frequency is less than 0. The derivative of BR with respect to frequency is greater than 0. Now recall that we said that one of our ideal situations was when BD was independent of frequency. That is, the susceptance of our active device was independent of frequency. Well, we're not going to achieve that for RF and microwave oscillators because of our parasitics. But in this particular topology, the variation of BD with respect to frequency even improves the performance of the oscillator by reducing the phase noise even further. So getting back to this point of intersection, the gamma R curve and the 1 over gamma D curve go past each other as fast as you possibly can imagine. So let's summarize what we've achieved so far. We have many more presentations to come. First of all, we've outlined a topology. We have shown a topology which is evolved from our modified Colpitt's common base oscillator configuration. We've replaced some of the elements in that standard design with elements having improved performance. One being the use of a transmission line instead of an inductor, and another is the use of stacked varactor diodes so that we have a more linear resonator network, which of course is tunable. Our initial design objective has been stated, and our goal is stable single frequency oscillation with low phase noise and high efficiency. So coming up, we're going to consider a more detailed design strategy, oscillator startup requirements, and strategies for avoiding multiple oscillations.